This paper delves into the fibers of the principal-minor map over a general field, concentrating on the relationship between two matrices with equal principal minors. The principal-minor map assigns to each n times n matrix the 2n vector of its principal minors. The primary objective is to determine the conditions under which the sole connection between two matrices with equal principal minors is diagonal equivalence. Reducible matrices, which can be written as block upper triangular matrices after permuting rows and columns, are an exception to this rule, as they may have equal principal minors without being diagonally equivalent. The paper also aims to characterize real stable matrices and answer a question posed by Borcea, Brändén, and Liggett. A real stable matrix is an n times n complex matrix A whose determinantal polynomial Fa equals det. A plus diag. x1. Xn, is real stable, meaning it has no zeros with strictly positive imaginary parts. In a previous work, the author and Vincent proved that if Fa is real stable for some complex matrix A, then there exists a Hermitian matrix H such that Fa equals det. H plus diag. x1, xn. Since the coefficients of Fa are the principal minors of A, the matrices H and A share the same principal minors. To fully characterize real stable matrices, the paper studies the structure of matrices that have principal minors equal to those of a Hermitian matrix. This is achieved by examining the principal minor map, which assigns to each n times n matrix the 2n vector of its principal minors. The paper provides a necessary and sufficient condition for the fiber of the principal minor map to be a point up to diagonal equivalence, improving upon conditions proposed by Hartfield and Loewy in 1984 and 1986, respectively. Furthermore, the paper establishes a connection between the reducibility of a matrix and the reducibility of its determinantal representation. This connection is used to fully characterize the fiber of symmetric and Hermitian matrices in the space of n times n matrices over any field F. Additionally, the techniques developed in the paper are applied to answer the question of Borcea, Brändén, and Liggett concerning real stable matrices. The principal minor map, denoted by phi, assigns to each matrix a vector of its principal minors. This paper focuses on studying the preimage of this map. The problem of characterizing the preimage dates back to 1980, when Engel and Schneider showed that a completely reducible matrix of belonging to the fiber of a symmetric matrix B must be diagonally equivalent to it. Subsequent work by Hartfiel and Loewy, as well as Loewy, has explored the fibers of general matrices over any field F. A matrix A is said to have a cut X subset of n if 2 is less than or equal to X is less than or equal to n2 and the ranks of A, X, XC, and A, XC, X, are at most 1. Loewy's result states that an irreducible matrix with no cuts has only one preimage up to diagonal equivalence. This paper extends this result, showing that irreducible matrices and irreducible symmetric matrices are the only matrices that satisfy this property. The main result, Theorem 4.1, states that the fiber of a matrix over any field F under the principal minor map consists of only one point up to diagonal equivalence if and only if the matrix is irreducible and either it has no cuts or it is diagonally equivalent to a symmetric matrix. This result enables the development of an algorithm to produce another point in the fiber when the fiber is not a point up to diagonal equivalence. Furthermore, the paper relates the structure of the matrix A to the factorization of its determinantal polynomial, characterizing the fibers of symmetric and Hermitian matrices in the space of n times n matrices. In particular, it is shown that a matrix A can be written as a block upper triangular matrix with S diagonal blocks if and only if its determinantal polynomial factors into S irreducible factors. This leads to the characterization of the fiber of an irreducible matrix under the principal minor map, which consists only of irreducible matrices. Finally, the paper presents a second main result, Theorem 6.2, which states that for a symmetric matrix A with entries in a field F, either the matrix A is irreducible and the fiber of A consists of all matrices that are diagonally equivalent to A, or A is completely reducible. The paper delves into the fiber of the principal minor map, focusing on the properties of matrices under this map. It begins by describing how a matrix can be written as a completely reducible matrix with diagonal blocks, and its fiber consists of matrices that can be written as block upper triangular matrices with irreducible diagonal blocks. This leads to the characterization of the fiber of an irreducible symmetric matrix, which consists of a single point up to diagonal equivalence. The paper then extends this to Hermitian matrices, showing that the fiber of an irreducible Hermitian matrix can be bigger but still consists solely of irreducible Hermitian matrices. Main result 3 provides a comprehensive understanding of the fiber of a Hermitian matrix, stating that it either consists of Hermitian irreducible matrices or can be expressed as a completely reducible matrix. The paper also addresses real stable matrices, defining them as matrices that can be written as block upper triangular matrices with diagonal blocks that are irreducible and Hermitian. Finally, it touches on the fibers of skew-symmetric matrices, mentioning that if two skew-symmetric matrices have equal principal minors of size at most 4 and one is dense without cuts, they are diagonally equivalent. The research paper builds upon previous works by the author and Vincent, which generalized the results of Odin and others on the orbit of the hyperdeterminant under the action of the group SL2, R, and Sn. The authors showed that the image of the principal minor map over arbitrary unique factorization domains can be defined by the vanishing of polynomials in the orbit of the hyperdeterminant. The paper introduces terminology and notations in Section 2, which are used throughout the paper. Section 3 states and proves the generalized Laplace theorem, utilized in Section 4 to construct a matrix in the fiber of an irreducible matrix with a cut, characterizing matrices with a single point fiber. The paper explores the structure of a matrix according to its determinantal polynomial, providing a description of the fibers of symmetric matrices and Hermitian matrices. The authors also described stable matrices. Notably, the set D, N, is defined as the set of all matrices A such that the fiber of A consists of matrices diagonally equivalent to A or at, where it denotes the transpose of the matrix A. The determinantal polynomial of a matrix A is defined as Fa equals det. Diag. x1, xn, plus A, a multiaffine polynomial. The rank of a matrix A is denoted by Rk, A, and the adjugate of A is denoted by Aj. The Rayleigh difference of a polynomial f with respect to two variables xi and xj is defined as increment ij, f, equals partial differential f, partial differential xi partial differential f, partial differential xj f squared f, partial differential xi partial differential xj, used to characterize multiaffine determinantal polynomials of symmetric and Hermitian matrices, as well as determinantal polynomials of n times n matrices. The paper's results provide novel insights into the structure of matrices, shedding light on the properties of determinantal polynomials and their connections to matrix fibers and stability. Theorem 2.1 establishes that a multiaffine polynomial f in variables x1, xn can be represented as the determinant of a matrix D. A is not diagonally equivalent to a symmetric matrix and has a cut X subset of n. This discussion underscores the importance of principal minors and their relationship with matrix A. The findings have significant implications for understanding the structure and properties of matrices, particularly in the context of reducible and irreducible matrices. The authors present a proof by contradiction to establish that matrix B is not diagonally similar to matrix A, assuming the existence of a diagonal matrix D such that B equals DAD minus 1. They define a matrix H and analyze its properties. This analysis yields a matrix C with the same principal minors as A. If C were diagonally congruent to A contradiction would arise, thereby implying that B is not diagonally equivalent to A. This result is achieved by switching factors in H's submatrices to obtain B. The authors then shift their focus to the structure of a matrix as revealed by the factorization of its determinantal polynomial. A crucial connection is highlighted. A matrix's irreducibility is intimately tied to the irreducibility of its determinantal polynomial. This relationship has significant implications for understanding the properties and behavior of matrices. The relationship between the irreducibility of a matrix A and its associated polynomial f, defined as the determinant of the sum of A and a diagonal matrix with variables x1, xn on the diagonal, is a pivotal concept in linear algebra. A key result, Theorem 5.2, establishes that A can be rearranged into a block upper triangular matrix with irreducible diagonal blocks if and only if f factors into irreducible polynomials. This theorem has profound implications for graph theory, where the matrix A corresponds to a directed graph G by contracting each strongly connected component of G into a single vertex. We obtain a new graph H that is a directed acyclic graph, allowing for a topological ordering of its vertices. This ordering corresponds to the diagonal irreducible blocks in the rearranged matrix A. A corollary further elaborates on this connection between the matrix A, its polynomial f, and the graph G, providing a deeper understanding of the interplay between these mathematical structures. In the context of matrix theory, a matrix A can be factored into irreducible polynomials f1, fs, where each phi is an element of f, xk, k element of t. The fiber of A consists of all matrices that can be written as block upper triangular matrices with S diagonal irreducible blocks A1, as such that the determinant of each I plus a diagonal matrix equals phi. For instance, consider a 6 by 6 matrix A, whose determinantal polynomial Fa can be factored into three irreducible polynomials. According to Theorem 5.2, this matrix can be written as a block upper triangular matrix with three irreducible diagonal blocks. Corollary 5.4 then implies that the fiber of A consists of matrices that can be written in a specific form, up to permuting the diagonal blocks and up to diagonal equivalence. Corollary 5.6 states that if A is an nxn irreducible matrix with entries in a field F, where n is greater than or equal to 4, then the fiber of A consists of irreducible matrices. The proof involves showing that if B is any matrix in the fiber of A, then the determinant of B plus a diagonal matrix is equal to F, which is irreducible by lemma 5.1. Hence, B is also irreducible. The paper then shifts focus to the fibers of symmetric matrices. Lemma 6.1 states that an nxn symmetric matrix A with entries in a field F, where n is greater than or equal to 4, belongs to the set D, n, if and only if A is irreducible. The proof involves showing that if A is reducible and symmetric, then it can be written as a block diagonal matrix with symmetric diagonal blocks, which implies that A does not belong to D, n. Conversely, if A is in D, n, then any matrix B with the same principal minors as A must have the same determinantal polynomial Fa, which implies that B is diagonally equivalent to A. The authors examine the fiber of the principal minor map, focusing on symmetric matrices with entries in a field F and n is greater than or equal to 4. They prove Theorem 6.2, stating that the matrix A is either irreducible with a fiber consisting of a point up to diagonal equivalence or can be written as a completely reducible matrix with reducible diagonal blocks. In the latter case, the fiber includes all matrices that can be written as block upper triangular matrices with reducible diagonal blocks, after permuting rows and columns. The authors utilize Theorem 2.1 and Lemma 2.2 to show that alpha ij equals alpha ik alpha jk for 1 is less than or equal to I less than j less than k is less than or equal to n, and construct a diagonal matrix D such that B equals DAD and A element of D, n. They then proved Theorem 6.2 by considering the cases where A is irreducible and where A is completely reducible with reducible diagonal blocks. Next, they restrict their attention to the field of complex numbers C and examine the fibers of Hermitian matrices. They prove Lemma 7.1, stating that the fiber of A consists of irreducible Hermitian matrices up to diagonal equivalence if and only if A is diagonally equivalent to an irreducible Hermitian matrix. This result is used to prove Theorem 7.2, characterizing the fiber of a Hermitian matrix A as either consisting of Hermitian irreducible matrices up to diagonal equivalence or consisting of matrices that can be written as block upper triangular matrices with reducible diagonal blocks that are diagonally equivalent to Hermitian irreducible matrices. The authors employ various mathematical concepts, including determinantal polynomials, reducibility, and diagonal equivalence, to establish their results. In the context of a research paper, the authors address a theorem that is omitted due to its similarity to Theorem 6.2. They note that, unlike in the symmetric case, the diagonal blocks of a matrix within the fiber of a Hermitian matrix A need not be diagonally equivalent to the diagonal blocks of A. This is exemplified by example 4.8 from 2. The authors then tackle question 1 posed by Borcea, Brändén, and Liggett, 5, regarding real stable matrices. A real polynomial f element of R, x, x, is considered stable if it has no zeros with strictly positive imaginary parts. A real stable matrix A is an n times n complex matrix with a real stable determinantal polynomial, i.e., f underscore A equals det, diag, x, x, plus A, is real stable. Corollary 7.3 is presented, stating that if A is an n times n complex matrix such that f equals det, x, x, plus A, is real stable, then A. If f is irreducible, then A is diagonally equivalent to an irreducible Hermitian matrix with equal principal minors. B. If f factors as ff, where each factor f is irreducible, then A can be written, after permuting some rows and the corresponding columns, as a block upper triangular matrix with S diagonal blocks that are irreducible and diagonally equivalent to Hermitian irreducible matrices that have determinantal polynomials equal to the irreducible factors of F. The proof of Corollary 7.3 is provided, relying on 2, Theorem 6.6, and Lemma 5.1 for Part A, and Theorem 5.2 for Part B. The authors conclude that each diagonal block is diagonally equivalent to an irreducible Hermitian matrix, as desired. The paper concludes with a comprehensive review of the fiber of the principal minor map, an essential concept in the study of matrices and their properties. It begins by citing Hartfield and Loewy's work on matrices having equal corresponding principal minors, 11, followed by Holtz and Sternfels' research on hyperdeterminantal relations among symmetric principal minors, 12. The authors then delve into the relationship between hyperbolic polynomials, interlacers, and sums of squares, as explored in Kummer, Plowman, and Vincent's study, 13. This is followed by a reference to Williamson's work on matrix canonical forms, 14, which provides a framework for understanding the structure and properties of matrices. Loewy's seminal paper on principal minors and diagonal similarity of matrices is also discussed, 15. Highlighting its significance in the context of this research. Oding's work on set-theoretic defining equations of the variety of principal minors of symmetric matrices is cited, 16, emphasizing the importance of algebraic geometry in this field. The paper also touches upon the concept of interlacing families, particularly bipartite Ramanujan graphs of all degrees, as studied by Marcus, Spielmann, and Shrivastava, 17. Finally, the authors acknowledge Rising, Kulesha, and Tasker's efficient algorithm for the symmetric principal minor assignment problem, 18, demonstrating the practical applications of these theoretical concepts. In conclusion, the paper provides a thorough overview of the fiber of the principal minor map, connecting it to various other areas of research in linear algebra, algebraic geometry, and graph theory. It emphasizes the importance of understanding the properties and behaviors of matrices and their principal minors, as well as the need for further exploration in this field.